we're done, we're cooked. When it comes to rate laws, we know what we need to know. We know the integrated rate law, we know the initial rate law method. We even know how to set up rate laws just based on delta concentration, delta T. So we've got 3 different ways we can set up rate laws and try to figure those out. So we're done. That's how we do it. That's how we do it experimentally. Great. Now let's see some other interesting facets about rates, and what we're going to see in a little while is mechanisms of reactions. First, we're going to talk about rates. What happens with kinetics and temperature? I haven't talked about temperature in all of this. No temperature in any of our equations. We've been using a lowercase t. Lowercase t is time. What are we doing about temperature? Does temperature affect the rate of our reaction? So just to be clear, all this stuff we've been doing for has always assumed, even though I never said it until now, that we're at a constant temperature, that we are not changing the temperature of our reaction during our reaction. And in fact, when you're doing kinetics types experiments, it's important to try to not change temperature unless that's your goal. And we'll see why you might want to have that goal in a moment. Just as a reminder, what is temperature? Temperature is a measure of the average kinetic energy of the system. If you have a low temperature, things are moving slowly. But if you have a high temperature, things are moving like this, bouncing off the walls, okay? So that's what we're talking about in temperature as measured of average kinetic energy of a system. Low temperature, slow. High temperature, very fast, thing bouncing off the walls, okay? That's going to make a difference to how we think about how temperature affects our kinetics. And you can kind of already get an idea of what's going to happen. Okay, so let's do some theory, right? We're just going to think about it, a Gedanken experiment. And so we're going to do our blue circles and our purple squares. We're going to react those again. And we're going to do it at a low temperature, and we're going to do it at a high temperature. And so we're just going to look at, say, this blue guy here. And a blue guy, at a low temperature, it means everybody's moving kind of slow. And so just a little while later, the blue guy has only moved from here to here. What are the chances that he's going to run across a purple square and bump into him if he's not moving very fast and the purple square is not moving very fast, right? It's pretty low, right? You're not going to see a bunch of people in slow motion running into each other and going, ooh, right? You know, even if they do it on purpose, it takes forever, right? Even if you get these great slow motion things of somebody running and, gosh, can you hurry that up? What happens if we do it at high temperature? At high temperature, everybody's moving around like crazy, they're bouncing off the walls. And so a short time later, the exact same short time we had in the slow one, everybody's moved around. They've bounced off of like 15 people already. What are the chances that they're going to react if they've had a chance to bounce off of 15 people? Much, much higher than if you bounced off of nobody. Okay? And so we're going to find that at high temperature, our rate should be higher. In fact, we might even guess much higher, right, if we're at a high temperature. But what is high? Are we talking, a degree? Are we talking 100 degrees, 1,000 degrees? Do we have to go to the sun before we get this effect? How high of a temperature change before we see, slow rate and fast rate? Okay. Well, let's look at some data. Here is some data somebody took, and what they did is at several different temperatures, they calculated the value of the rate constant. Now, I'm not talking about rate in particular here, but I am talking about rate constant. And the rate constant is directly proportional to the rate, right? Because when you have your rate law, you have rate equals k times a to the m, right? So the higher the k, the higher the rate. And so we're going to plot these k's as a function of temperature in order to see what they do. And you can see very, very clearly that at low temperature, I have a low k, and my reaction is relatively slow. Not slaw. It's not coleslaw. It is slow. And at a high temperature, I have a very high k, and my reaction is going to be comparatively fast. I don't know if this is actually fast or if it's not. I mean, we might be comparing 1,000,000 years to 1,000 years, right? Still very slow from our lifetime point of view, but still a whole lot faster than something that happens in 1,000,000 years. Okay, so slow versus fast. And what's crazy is you look here at the table of data, and what do you have? At 20 degrees Celsius, you've got 2 times 10 to the minus 5th for k. At 60 degrees Celsius, so 40 degrees temperature difference, you've got 2.9 times 10 to the minus 3rd. 2 orders of magnitude. You've increased the speed of this reaction 2 orders of magnitude, 100-fold speed increase by changing the temperature just by 40 degrees. And so we can see there's a really high sensitivity of the speed of reactions to temperature change. This 10 degrees right here just went from 2.0 times 10 to the minus fifth to 7 times 10 to the minus fifth. That's almost a factor of 4 increase. So 10 degrees. The general rule of thumb, if people are just guessing, they have no data whatsoever, is about every 10 degrees Celsius that you change the temperature of reaction, increasing, you're going to double the rate of reaction. So going from 20 to 30, if you were just guessing, your rate of reaction would double from 20 to 30. If you were guessing from 40 to 50, your rate of reaction would double from 40 to 50. It's not an exact and hard and fast rule, but it's kind of a rule of thumb that people use. But that's a huge change, and honestly, that should really surprise you. I mean, 2 orders of magnitude, 100-fold faster in just 40 degrees. Why is that? What is happening on a fundamental molecular level in order to get changes that are that incredibly large? And as you might guess, that's what we're going to talk about next. So, what's going on? What is going on here to have these huge changes? So we're going to do this in the context of an example. We're going to have an example reaction, and we are going to try to figure out what variables affect whether that reaction is going to happen. So we're going to consider the reaction NO plus Cl2 goes to make NoCl plus Cl dot. And if you haven't seen this dot notation before, that dot means, it's not a minus sign, by the way, I'm going to make that a little clearer. It's a dot. It means you have a radical. It means you have an unpaired electron. If you've ever heard the term free radicals, people say, oh, I'm using this cream to get rid of the free radicals. Right? A free radical is just a molecule with an unpaired electron. So this Cl has an unpaired electron. It's got an uneven number of electrons. The reason people care about free radicals is they are very reactive, right? Because everybody likes to have their octet. And so if you've got something that's a free radical, it's going to be out there looking for things to react with to make itself happy. Now, that doesn't mean that you need to get rid of all free radicals in your life. They're good too, because they will react with bad things. And so it turns out some of the free radicals in our body will actually do things like prevent you from getting diseases and stuff like that. As with all things in life, moderation is the key. Not too many, not too few, and you're probably doing just okay. All right, so let's look at this reaction. I'm going to draw some very simple things. I'm not going to draw correct Lewis structures here. I'm not going to count all my electrons. I'm just going to say we've got an NO, an N-O, and we've got a Cl-Cl. And what are we going to do with that? Well, if you look at it, I'm just adding a Cl to my NO to get my NoCl, and I'm taking a Cl away from there. And so essentially what I'm doing is I'm breaking this bond right here, and I'm pushing that guy over onto that one. And so it looks something like this. When you look at the products, you get ONCl and you get Cl dot. Okay. Now, some interesting things is if you do the Lewis structures and things like that, right? NO, 2 elements, it's linear. ClCl, 2 elements, it's linear. ONCl is actually a bent molecule. So it doesn't look like this. It looks like, erase, thank you, ONCl. You've got that lone pair on the nitrogen, and then you end up with this bent molecule. And again, I'm not showing double bonds. I'm not showing all my lone pairs. I'm just kind of giving a visual indication of what's going on. So if you've got this going on, what's going to make this reaction go? Okay. What we have to do is we have to form that product. We have to form that bent product from these two straight things. And so we're going to say, hey, what happens? Let's actually literally think about the orientation and how these guys approach each other. If NO approaches Cl like this, okay, are we going to get a reaction? So, question mark. Are we going to get a reaction? It turns out, you're like, well, if they hit each other, isn't it going to react? Right? These guys, we're actually talking now about the actual molecules and their orientation in space. If this one's coming this way and this one's coming this way and they collide with each other, don't they have a nice chance of reacting? And the answer is no. These have a very low probability of reacting. You're like, why is that? Why is there a low probability? Don't we just make some NoCl? And the answer is because if you look at the structure of NoCl, what is the chlorine bonded to? The chlorine is bonded up here directly to the N. And if these two guys are coming at each other this direction, what is that chlorine going to do? It's going to bounce off an O. And if I'm hitting an O, am I likely to react with a nitrogen? So the answer is no, right? I'm not likely to make this reaction because I'm not hitting the thing that I want to hit. Okay? So you're like, well, let's just do that. We can fix that really easily. Let's just flip this guy around. And now we're going to have it facing the other direction when our chlorines go. And then this one comes this way, this one comes this way, and bam, we should get a wonderful reaction. And this also has a low probability of reacting. What? How can I have a low probability of reacting to? Well, you just said that the reason the first one didn't react is because I wasn't hitting the right atom. I turned this thing around, I'm hitting the right atom, and you're telling me the same thing? What's up with that? Well, it turns out that in order to make a wonderfully bent product like this, what the reaction really is asking us to do is start with something that's already bent. So these two colliding here and coming next to each other, they're bouncing off each other perfectly straight. And they're like looking, think, you know, you're expecting me to make an angle and you're putting me perfectly straight? I don't want to do that. And it turns out if you start to look at the molecular orbitals and the shape of the molecular orbitals, there's not enough electron density overlap to make that bond happen if you put them in the wrong orientation. So even that has a low probability of reacting. So what do I need to do in order to get these guys to react? Is I need to make their reaction look as much like the product as possible. I'm going to write that down. Make the reaction look as much like the product as possible. So darn it, if you're telling me I've got to make this bent ONCl, then what I want to do is I want to have a reaction where my ON approaches my Cl, where the Cl hits the N and is already at the right angle. So this guy is coming this way, this guy is going off to the left, and when they hit, boing, they're already making that angle that they're supposed to make. And when they're most likely to react is pretty much, not 100%, but pretty much when they look exactly like they're supposed to look when they're done. And that's a neat thing. So this one has a high probability of reacting. And again, these highs and lows are just relative to one another, okay? An individual reaction tells you the probability of it overall reacting, but comparatively, the orange one has a very high probability of reacting compared to either the blue one, where we had the right orientation but the wrong angle, or the red one where we had the wrong orientation and it just wasn't hitting the right molecule. All right, so orientation effects, great. This is what we call orientation effects. The rotation of molecules, the conformation of molecules. You want to start talking about catalysis and enzymes and things like that. All of that has a lot to do with orientation, how things are pointed when you're trying to make that reaction. Huge changes in probabilities of reaction. Like, great, huge changes in probability of reaction. That's just what we saw in temperature. So let's think about it. Is temperature going to affect our orientation effects a lot or not so much? Well, what does temperature do? Temperature makes things move faster, right? They make them bounce around and turn around more, okay? However, they're always bouncing around and turning around. When you have this reaction, you have that NO is constantly just flipping around in the air, whether we're in the gas or we're in solution, whatever. That NO is tiny. He's just kind of flipping around and moving around. Now, when he's flipping around, moving around at low temperatures, he's doing that. You might think, well, if he's moving around really slow, then it's not very often that he gets into the right orientation, so it might go slow. But when he's moving around really fast, right, he's rotating, and like many times every second, he's in the right orientation to react. You'll think, okay, great. So I've got this thing at low temperature. It's not going to do it much. At high temperature, it is. That explains my rate data that I just got. And you would be wrong, unfortunately, to think that. Why? Well, because you don't just look at how often it's in that right orientation, but how long is it spending in that orientation, right? If I'm spinning around like this, yes, I might hit the right orientation 1,000,000 times per second, but I'm only there for 1/10,000,000th of a second. And that's not very much time to react. Whereas if I'm moving slowly, yes, I'm maybe only hitting it, I'm just going to make up a number, once per second, but guess how long I'm spending there? 1/10,000,000th of a second. And it turns out there's very little effect, if you do the statistics, on how likely we are to be in just the right orientation at just the right time, whether we're moving fast or we're moving slow. And so these have low effects from temperature. They're very important effects, but they aren't affected by temperature much. Okay, so these orientation effects probably are not going to be the thing that fixes our problem and says, this is why K goes up so quickly with temperature. So let's look at another pretty obvious one once I say it to you, is if you want things to react, what's the first thing you might need, other than having those things, right? Is you need them to hit each other, right? And if you think about the kinetics of this thing, right? If we're moving slow, we said that these things are not going to be moving very fast. They're not going to hit each other very often. And if we're moving fast, they're going to hit each other all the time, right? Great. So collision frequency seems like there might be an effect there. Okay? So collision frequency. The faster you're going, the more you're going to be hitting with each other. Okay? Well, it turns out that's not it either. Why? You're like, come on. Collision frequency, the faster you go, the more often you hit, right? And that does certainly affect it, but not as much as you think it does. And I thought I had some numbers here. Let me pause for a moment and look for my numbers that I thought I had in this slide that I don't see right now. Okay, so let's figure out collision frequency. I found my numbers. What's happening here? Okay, well, I'm sure you remember this, that if you're trying to calculate the root mean square speed, and we use U for that, of a molecule in the gas phase, and we're just going to use the gas phase because it's easy, you get 3 times RT over M, where M is the molar mass in units of kilograms per mole. The kilograms there to cancel the kilograms that are inherent in the units of R. So what we're going to do is we're going to look at what happens to collision frequency as we increase the temperature by, I don't know, let's say 10 degrees Celsius. So we're going to say, hey, let's look at the root mean square speed at 308 Kelvin. And we're going to compare that. I'm going to divide the two by the root mean square speed at 298 Kelvin. And if you'll notice, right, a bunch of things are going to cancel. Our 3R's are going to cancel, our M's are going to cancel. And we're just going to get this URMS at 308 compared to URMS at 298 is just going to be the square root of the temperature differences, or not temperature differences, of the temperatures themselves, or just 308 over 298 square root. All right, my units drop out because my kelvins cancel. And you're like, okay, well, let's calculate that, put that in my calculator. What do I get? I get about 1.017. And what this tells me, if you look at that number, the 1 just says, hey, you didn't go down, you went up, right? Because we're above 1. That ratio is above 1. The speed went up. So 1.017 tells me that I get about a 2% increase in speed when I increase the temperature by 10 degrees Celsius, from 298 to 308. And you'd get a roughly similar thing whether you went from 350 to 360 Kelvin or even 700 Kelvin to 710 Kelvin. It's not going to be huge. The only time it would be huge is if you went from 1 Kelvin to 11 Kelvin, but we're not going to be talking about things happening on that scale. So we get a 2% increase in speed. A 2% increase in speed basically means a 2% increase in collisions. And a 2% increase in collisions is not the same as a factor of 2. Because remember, a factor of 2 is the rule of thumb. Right? A factor of 2 in the speed is a 200% increase. And of course, what we're saying is that the speed is only contributing 2% of this thing that we know from experimental data is actually a 200% increase. So it's a really good theory at first when you think about it. You're like, oh yeah, the faster we move, the more often we hit, and that's going to explain why we're getting these huge changes in rate as a function of temperature. But it's not, because it really is. It's actually a relatively small change, 2% for every 10 degrees Celsius. Not going to be causing huge changes in our overall ability to react. So gosh darn it, it's not collision frequency. It's not that orientation. What else could it be? It turns out there's one other important thing in what we call collision theory, which is what we're talking about now. Collision theory says that in order for things to react, they have to hit, right, collision frequency, with the right orientation effects, and enough energy to react. So let's look next at the energy of collision. All right. Energy of collision. We're going to get a huge change in the average energy of collision. We had a 2% change in our speed, right? And if you remember from your physics class, E equals 1/2 mv squared. Turns out if you get a 2% increase in your speed, you're going to square that, and you're going to get yourself a 4% increase in energy. A 4% increase in energy does not sound to me like it's going to get me a 200% increase in rate of reaction. Right? 4% and 200%, they're pretty far off of one another. So is it going to be the energy of collision? And it turns out it is. Oh, you frustrate me with your press comments. Why? Why is it that this relatively small change in speed doesn't change the collision frequency, but you're telling me, oh, it changes the energy enough to make a huge effect? It doesn't. I mean, it's 2% squared, that's 4%, that's nothing. And you'd be very sound in making that conclusion, because just based on this equation, you'd be right. Because remember, this equation, that URMS, root mean square, that's the average speed of a molecule. It's not saying the fastest one's the slowest one. It's just saying if I take all of them together and I average it out, that's what it's going to get to me. But it turns out the average isn't what's important in this case. It's not the average particle that's reacting. It's the super cool particles that are the ones reacting. What do I mean by the super cool particles? Well, if you remember, hopefully you did this in your Chem 50 class, is you had some sort of probability, I need there, and speed. And you said, hey, if I've got a gas, and I'm just looking at the distribution of speeds, right, at room temperature, the average speed of an oxygen molecule is about 500 miles per hour. But there's some oxygen molecules moving at 20 miles per hour, and there's some oxygen molecules moving at 5,000 miles per hour. But the root mean square speed, about 500 miles per hour. But we can look at a probability graph and say, what's the likelihood of any given speed? And let's just make up one, and it looks something like this. And the important part I'm going to show you here is this long tail way out here. This long tail says we've actually got some particles that are moving extraordinarily fast, right? If they're moving extraordinarily fast, we still have E equals 1/2 mv squared. So we've got some particles with very, very high energy. And what I'm going to do here is I'm going to put a mark. I'm going to say, hey, look, ding, this is the energy required to react. You've got to have at least that much speed, and right, speed 1/2 mv squared, you've got to have at least that much energy in order to react, which means if a molecule at this speed hit NO and Cl2, there wasn't enough energy to react. And why is that? Why is there a minimum energy to react? Well, part of it, there's lots of good reasons, but part of it is in order to react, you've got to take that Cl2 molecule that's pretty darn happy, and you've got to eject that Cl. So that NO's got to come up and it's got to hit that Cl hard enough that it ejects the Cl on the other side. That takes a bit of energy. You're not going to walk up to it and say, "Pardon, I don't mean to disturb you. I know we're in a library. I don't want to disturb you, but could you please get rid of that other Cl?" It's not going to work. He's really happy with that other Cl. What you have to do is you have to thwack him, right? You know, thwack him and make him just bounce off that other Cl. Enough energy to react. Okay, what does this have to do with temperature and kinetics, Professor Clements? Get to the point. I know this is a really, really long path to the point, but all this information is really useful when we're thinking about what's happening on a molecular scale. So, what's the point here? What happens when we change temperature? Well, when we change temperature, we saw the average speed went up by a very small amount. So let's increase our temperature by roughly 10 degrees Celsius. And we're going to find the average speed is going to go up by only a little bit. So we're going to draw this curve. And that peak is actually the average speed. So, right, you can see it only went up by a little bit. But one of the things that happens is this curve flattens out a lot. And when you increase the speed, although your average speed only increases a little bit, the number of particles you have at very high speeds actually increases quite a lot. And all of a sudden, the amount of particles we have beyond this energy required to react is much larger in this blue curve than it was in the red curve, where it was fairly small. And in fact, for every 10 degrees, you get roughly double the number of particles past some of those high energy posts. Right? So that trailing end there, those high energy, those super particles, are actually the ones doing all the work. Okay? So they're in a group work situation, they're doing all the work, these other guys are just sitting there doing nothing. Okay? And that's what's happening. When we increase the temperature of a system, we are increasing significantly the number of molecules that have sufficient energy required to react. We're not changing the collision frequency enough. We're not changing the orientation effects enough. We are saying, hey, I've got more particles with enough energy. So now we finally explained it. We said, okay, now we have a reason, even in collision theory, as to why our rates double roughly every 10 degrees. Obviously, the details have to be from the data, but we have a reason for that, and that's great. All right, so let's see if you were listening to our talk on collision theory, and you're going to try to apply this to something you've never seen before. Isn't that fun? If you're going on to organic chemistry, this is a useful thing to think about. I want you to look at these 4 pictures, and you tell me which of the following orientations would be most likely to yield the product in this reaction. Now, in order to know that, I encourage you to practice your Lewis structures and draw the product, to draw C2H6 out, because it'll really help you figure out what's going on in this one. So this one might take you a few minutes. It might take a little bit of thought and like, what is he asking for exactly? But go for it, try it out, and see where you end up. What did you come up with? Well, hopefully, when I said, hey, you should try drawing a Lewis structure, you came up with something like this for C2H6. 2 carbons attached to each other, each carbon has 3 hydrogens. And you compare it to what we're starting with. Each carbon only has 1 hydrogen. So what does my reaction need to do? My reaction needs to make sure that I add 1 hydrogen to each carbon. Right? Because here I've got 3 carbons on each hydrogen. Here I've got 2 carbons on each hydrogen. I need to add 1 hydrogen to each carbon. So if you remember a couple slides ago, I said the best way to get your reaction going is to make your reaction look as much like your products as possible. So if I've got a reaction where I need to have these 2 extra hydrogens on each carbon, my best reaction, my most likely and favorable orientation for that reaction is one where the hydrogens are already set up to be where they need to be. And so if I look at this first one, I've got a hydrogen hitting the end here, and that's great to add a hydrogen to that guy. But then what would have to happen? This hydrogen would have to magically migrate around the world, right? Because it's not like he can sense anything, and eventually find his way over to that side. And it's possible, but it's probably going to take a while. I mean, you got 3-dimensional space, things What are the chances? Pretty low. All right, so probably not A. How about B? Well, we look here, we've got this hydrogen going to here, but what's it going to do? It's only hitting this side. And so it's going to try to add 2 hydrogens to that side, which is not possible. And so, again, we're going to have that situation where maybe 1 hydrogen adds and then 1 has to float around. It doesn't seem a very likely scenario to me, so we cross that one off. Let's look at the next one. We've got this H going end on into there. And like, he's not even like attacking one of the carbons, right? He's like trying to attack the middle of that thing. And maybe it'll be successful. Maybe it'll kind of knock through the thing. Maybe it'll attach to one. But again, you've got this problem that this other H is just going to be kind of flying out there and eventually having to find that other carbon. That's probably not it either. It better be this last one, right? What is this last one? One H attaching one carbon, the other H attacking another carbon. One adding to the top one, one adding to the bottom one. If they literally come into each other just like that at that orientation, that's going to be your most likely way of having that reaction work. And this is a lot of how organic chemistry works, is you have to think about these orientation effects, and there's charge effects and electrons moving and things like that. But it's a lot to do with, does my reactant look an awful lot like my product? If so, I'm probably doing pretty good. And so in this case, it's going to be D, is that's the most likely orientation. So how are we going to draw this? How are we going to draw all these effects from collision theory? Well, you've probably seen these things before. We're going to draw potential energy diagrams, energy versus reaction coordinate. Right, and that's just that reaction progress is another way that people will do it. We start with our reactants at a given energy, right? And that might be, N2O5, or it might be anything else, reactants. And then we're going to go to our products. And there's different types, right? Sometimes our products are higher in energy. Sometimes our products are lower in energy. It turns out for our NO plus Cl2 reaction, our products are actually much higher in energy. NOCl plus Cl dot. Those free radicals, very, very high in energy. So we're actually increasing our energy. And, depending on what you studied in your previous classes, you might have just drawn a line up there that says, hey, I'm going to join those. And in order for my reactions to turn to my products, it's kind of like a marble. I've got to roll the marble up that hill and give it enough energy to get to the top of that hill. And that's a fine way of thinking about it. But it turns out that's not entirely true. Most reactions, not only do you need to put the marble just to where it needs to be, but oftentimes you need to put the marble a little bit higher. And so in fact, the reaction coordinate diagram looks a little more like that. There's this additional energy that you had to do. You had to break that Cl bond, right, which took a lot of initial energy. You might have gotten some of that back when you made that other bond in the new molecule. So that's why our products are a little lower than that peak value. But right, we had to put in a lot of energy to get that reaction to run. So that might be what we call a reaction coordinate diagram. This is for an endothermic reaction, right? If you remember, endothermic means it absorbs heat. You need to put heat into the reaction in order to get it to run. And the other thing we're going to talk about on this particular graph is the activation energy. So my orange goes from the top of this bubble here all the way from the reactants. We're going to call this EA, or activation energy. And all reactions have an activation energy. Some of them big, some of them small, but all reactions have an activation energy. And we have to get over that activation energy in order to make it go. If we roll our marble this high, that marble is just going to roll right back down. So even though we've surpassed the energy of our products, we don't have enough energy to make this reaction run. And that's really important for understanding, especially exothermic reactions, which we'll do in a moment, that don't run spontaneously. Like, if it's exothermic, isn't it just going to run spontaneously? And the answer is no, and it's always from these reaction barriers. So that's what it might look like for an endothermic reaction. Always the activation energy is from the reactants to the top of this here. And so that's where it is. It's always to the top of that one there. If we have an exothermic reaction, then we have a case where our products are lower in energy than our reactants. So we're going to do energy here, and then this is reaction coordinate on this axis. And again, depending on who you had and what kind of class you took, for Chem 50, Intro Chem, you might have drawn something like that. But that doesn't explain why some reactions don't happen. If I turn on methane gas, right, the gas on your stove or in lab, we have those methane gas things, and I just turn it on, I just sit there, is anything going to happen? And the answer is no, right? It's not going to just light itself. You're like, well, yeah, my stove lights itself, right? It's got a pilot light or it's got a clicker in there that's doing that. But if you just sit there with nothing to light it, it's just going to sit there essentially forever and never react, even though it would like to, because this energy is lower at the end than it is at the beginning. And why is that? Well, because it turns out it's not that blue one, it's this red one, and there's a barrier in order to get this thing to start reacting. And you might have talked about that before. But the trick is, where does that barrier come from? Why is there that barrier in the reaction? And that barrier usually comes from the fact that you have to break bonds, right? In order to get two molecules to react, you got to start breaking bonds in one molecule. So before you get this really, really nice effect of, oh, I made these new bonds and they're really low in energy, I've got to undo existing bonds. And right, if you have an existing bond, it means that bond has some energy to it, and it's not going to be like just easy to break. Some are easier, some are harder. There's going to be some impediment to your breaking that bond, and that's our activation energy. So just like we had above, the activation energy is always from our reactants to the top of this curve, right? And the top of that curve is called the transition state. It's the very dot at the top of that curve. And it's called the transition state because it's the transition state between the reactants and the products. It's the highest energy point. And activation energy, EA, is always from the reactants to the highest energy point on the transition state and then down, whether you're in an endothermic reaction or an exothermic reaction. And so it turns out what you're going to find is that the speed of a reaction depends a lot on the size of that activation energy barrier. One other thing I want to point out before I talk about that a little more is you probably also did on your previous things that the difference between the reactants and the products energy level is delta H. And that's unrelated to activation energy, totally unrelated to activation energy. You can have a very large delta H with a small activation energy. You can have a large delta H with a large activation energy. They are both measured from the reactants side, and so they don't affect one another directly. So what do I mean that activation energy is going to affect how fast the reaction is? Well, imagine an activation energy with very, very small. And you can even think about this as you were walking down the street, there was a marble that you had to step over, right? You could continue walking down the street because a small activation barrier like a marble is very easy just to step over. And so your reaction rate of walking down the street is going to be still very, very quickly. There's this barrier, you got to go over it, but that was a pretty easy barrier to go over. But you're walking down the street and there's an 18-foot chain link fence with like razor wire on top. And you look at that thing and you're like, that is an activation barrier. I cannot go over that. I just don't have enough energy. I could try climbing that thing, but I just don't have enough energy to try and make it over that razor wire or cut it. I'm not going to progress. And so you're going to find that your reaction's not going to go. You need like those superhuman people who can do those kind of races and do that crazy stuff, which is very few and far between. Right? So our activation barrier is going to affect a lot the speed of reaction. Most people have heard the De Beers slogan for diamonds, that a diamond is forever. But it's actually untrue. Diamonds are unstable at atmospheric pressure, and they are naturally degrading back into graphite, which is the most stable form of carbon at room temperature. But no one ever worries about their diamonds turning into graphite, even though it's happening spontaneously. And why is that? Well, it's because it turns out that even though it's spontaneous, it is energetically favorable, and it will happen eventually. The activation barrier for doing that is extraordinarily high, so very few carbon atoms at any given moment of time are doing that. So yes, a diamond will eventually convert into graphite, but it takes, I think, on the order of 400,000 or 500,000 years. And a slogan of a diamond is 400,000 years just is not as nice as a diamond is forever, and so they have that slogan instead. So we now know a little bit about activation barriers. We know a little bit about collision theory, how orientation effects, how energy and collision frequency affect the ability of reactions to happen, and we're starting to look more on a molecular level. Next thing we're going to talk about is the Arrhenius equation, which relates our activation energy directly to our rates of reaction, which is really cool. Thanks for listening. Bye-bye.